On September 15th, 2017, a spacecraft the size of a school bus, screaming through space at 111,000 kilometers per hour, fired off its final transmission to Earth from deep inside the atmosphere of Saturn. And buried inside that last signal, hidden in data that scientists would spend years cracking open, was something nobody on Earth had predicted. Not aliens, not a message. Something in many ways stranger than either of those things. A set of measurements captured in the final 91 seconds before the spacecraft was torn apart that directly contradicted the model scientists had spent 30 years building to describe Saturn's rings and its atmosphere. Data showing that the narrow space between Saturn and its rings, a region considered so hostile and unpredictable that no spacecraft had ever dared enter it before, was not the chaotic, debris-filled killing field engineers had feared. It was quieter than expected, more structured, and it was carrying things that had no business being there. Things that are still being explained. Things that pushed one of the senior scientists on the mission to write, in a peer-reviewed paper published in Science, that the findings were difficult to reconcile with any known process. Difficult to reconcile with any known process. That phrase, coming from a scientist who spent decades staring at Saturn, is worth sitting with, because it means the instruments on that spacecraft worked flawlessly. The data they returned was clean and reliable, and what that clean, reliable data revealed was something the best models of Saturn's behavior, built on the best physics we understand, simply cannot produce. This video is about what that spacecraft actually found in its final moments, in its final months, and in the years of forensic data analysis that followed its death. Not invented patterns, not AI hallucinations, not cover-ups. The real findings, the ones that appeared in peer-reviewed journals, the ones cited by planetary scientists today, and the ones still driving brand new questions about Saturn and its moons. Subscribe right now and hit the notification bell before this video ends. Because the real story of what this mission uncovered is one of the most extraordinary chapters in the history of planetary exploration, and the last chapter has not been written yet. To understand why the final data was so unexpected, you first need to understand what everyone thought they already knew going into those final 22 orbits. The spacecraft arrived at Saturn in July 2004 after a 7-year journey from Earth. Over the following 13 years, it completed 294 orbits of Saturn, flew past the moon Titan 127 times, performed 23 close flybys of the moon Enceladus, and beamed back more than 450,000 images along with an enormous mountain of scientific data. It was, by any reasonable measure, one of the most productive planetary science missions in history. And by 2017, when mission planners decided to end it by plunging the spacecraft into Saturn's atmosphere, a deliberate act designed to make sure it could never accidentally crash into one of Saturn's potentially life-bearing moons and contaminate it, scientists genuinely believed they had a reasonably complete picture of the Saturnian system. They knew about the hexagonal storm at Saturn's North Pole, a persistent six-sided atmospheric feature stretching roughly 30,000 kilometers, first photographed by the Voyager spacecraft in 1980, and still spinning there 24 years later when this mission arrived. They knew about the extraordinary complexity of Saturn's ring system, the way the rings are divided into named bands, the way gravitational interactions with Saturn's moons carve out gaps and sculpt razor-sharp edges, the wave patterns that ripple through the ring material like something dropped into a pond. They knew about the water geysers erupting from cracks in the southern pole of Enceladus, a discovery made in 2005 that completely rewrote scientific thinking about where in the solar system conditions for life might exist. What they did not know was what was actually happening inside the narrow gap between Saturn's innermost ring and the top of its atmosphere. That region, roughly 2,000 kilometers wide, a distance that sounds huge but is basically nothing compared to the scale of Saturn itself, had never been directly sampled. It was assumed to be packed with small ring particles, potentially deadly to any spacecraft passing through it at orbital velocity. The original mission design had kept the spacecraft well clear of this region throughout its 13 years of operation. In the final phase of the mission, called the grand finale, mission controllers took the calculated risk of sending it through that gap. 22 times between April and September 2017, the spacecraft dove between the rings and the atmosphere, and what its instruments found inside that gap was not what anyone expected. Before the grand finale orbits began, mission scientists ran models of what the ring-atmosphere gap probably contained. The models predicted a region relatively dense with small particles, debris shed from the inner rings, charged dust grains, and other material that would need to be carefully navigated to protect the instruments. The spacecraft was oriented with its high-gain antenna pointing forward during the first ring plane crossing, using the dish as a physical shield against anticipated particle impacts. When the data came back, the particle count was dramatically lower than expected. The gap was cleaner than the models had suggested. And this was not a minor discrepancy. The models were predicting particle densities that would have made the environment genuinely hazardous, and the actual measurements showed a region that was surprisingly clear. This finding mattered in two ways. Practically, it meant the gap could be used more freely than planned, which is why mission controllers felt confident enough to send the spacecraft through it 22 times rather than a more cautious number. Scientifically, it meant the models describing what happens at the inner edge of Saturn's ring system were wrong in a fundamental way. Something was keeping the gap cleaner than expected. Some process was actively removing or preventing the accumulation of particles in a region where the model said they had to be present. That process was not immediately identified. Several explanations have been proposed, including electromagnetic effects from Saturn's magnetic field, sweeping charged particles out of the gap. But the question of what is actually keeping the gap clean against the constant inward drift of ring material remains an active area of research to this day. The second surprise was stranger, and it is the one that showed up in those peer-reviewed papers with language like difficult to reconcile with any known process. As the spacecraft made its grand finale passes, its ion and neutral mass spectrometer, an instrument built to identify the chemical composition of whatever gas or particles it encountered, was sampling the thin material inside the gap between the rings and Saturn's upper atmosphere, and it was finding things that did not belong. The instrument detected complex organic molecules, not simple hydrocarbons like methane, but larger, more complex compounds with molecular masses high enough to suggest structures that do not form easily in the environments where they were being detected. Organic compounds of this complexity require very specific chemical conditions to assemble, conditions involving particular temperatures, pressures, radiation environments, and specific precursor molecules reacting over long enough timescales. The gap between Saturn's rings and its atmosphere does not obviously provide any of those conditions. The temperature is brutally cold, the pressure is near vacuum, and the radiation environment from Saturn's monstrous magnetic field is intense enough to shred complex molecules rather than build them. Finding complex organics there was unexpected. In the same way, finding a complicated piece of machinery in the middle of an empty desert with no roads and no tracks leading to it is unexpected. The object is there. The mechanism by which it arrived or assembled there is not obvious. The principal investigator for the ion and neutral mass spectrometer, a senior research scientist at the Southwest Research Institute, described the findings with real astonishment. The material flowing into Saturn's atmosphere from the rings was not the simple water ice everyone had assumed. It was a complex cocktail. Water, yes, but also organic compounds, silica particles, and other materials whose presence suggested the rings are chemically active in ways nobody had previously understood. Scientists proposed the complex organics might be forming in Saturn's rings through photochemical reactions, sunlight-driven chemistry acting on simpler molecules over vast timescales. But the complexity of what was found exceeded what those models could produce. The gap between what the chemistry models predicted and what the instrument actually measured is real, documented, published, and not yet fully resolved. Then there was the matter of the silica particles. Fine-grained silicon nanoparticles, the same kind of material that makes up certain types of terrestrial rocks and sand, were detected inside the ring atmosphere gap. Their presence pointed toward a process of erosion, material being ground down into nanoscale particles by impacts within the ring system. But the distribution and abundance of the silica did not match what the erosion models predicted, adding yet another dimension to the chemical inventory the models had completely missed. The flow of this material from the rings into Saturn's upper atmosphere is called ring rain. The term was actually coined long before this spacecraft measured it directly based on indirect evidence, but what was measured directly during the final grand finale orbits showed that ring rain is heavier, more chemically complex, and more variable across latitude than any previous model had described. The third surprise came from Saturn's magnetic field, and this one has implications that reach far beyond ring chemistry into fundamental questions about how planets generate their magnetic fields in the first place. Every planet in the solar system that has a significant magnetic field, Earth, Jupiter, Saturn, Uranus, Neptune, generates that field through the motion of electrically conducting fluid deep inside it. On Earth, it is the molten outer core, primarily liquid iron, churning in patterns driven by heat flow and the planet's rotation. On the gas giants, it is electrically conducting fluid hydrogen, hydrogen compressed under such extreme pressures deep inside the planet that it behaves like a metal conducting electricity and generating magnetic fields through its motion. A fundamental feature of any magnetic field generated this way is that the field's axis, the imaginary line connecting the north and south magnetic poles, should be tilted relative to the planet's rotation axis. On Earth, the magnetic poles are currently offset from the geographic poles by about 11 degrees. On Jupiter, the tilt is roughly 10 degrees. On Uranus and Neptune, the tilt is dramatic, more than 50 degrees away from the rotation axis. Saturn is different. Saturn's magnetic field is aligned with its rotation axis to a level of precision that is, in the words of the researchers who measured it, extraordinary. Before this mission, the alignment was known to be close, within about 1 degree. That alone was already puzzling enough to trigger theoretical work on why Saturn's field behaved so differently from every other planet. The grand finale measurements taken as the spacecraft dove repeatedly through the region where the field is strongest produced the most precise measurement of Saturn's magnetic field alignment ever made. The result was shocking. The tilt of Saturn's magnetic field relative to its rotation axis was less than 0.0095 degrees, not even 1/100th of a degree. The principal investigator for the magnetometer instrument at Imperial College London described this finding in her published papers as posing a fundamental challenge to every existing model of planetary magnetic field generation. The standard theoretical framework, called magnetohydrodynamics, which describes how conducting fluids generate magnetic fields through their motion, contains a mathematical rule called Cowling's theorem, which states that a perfectly symmetrical, perfectly aligned magnetic field cannot be sustained by fluid dynamo action. Something has to break the symmetry. Something has to tilt the field at least slightly away from the rotation axis. Saturn's field appears to defy this constraint. It is not perfectly aligned. The measurement has uncertainties, and there are likely small asymmetries the current instruments cannot resolve. But the alignment is so close to perfect that explaining it requires proposing mechanisms that have no confirmed precedent in planetary science. One hypothesis involves a layer of electrically conducting fluid at an intermediate depth in Saturn's interior that is somehow suppressing the tilt through helical convection. Another suggests differential rotation, layers of the planet rotating at slightly different speeds, is smoothing out the asymmetries. Neither hypothesis is confirmed. The question of why Saturn's magnetic field is so precisely aligned with its rotation axis remains one of the genuinely open problems in planetary science as of 2026. None of the findings above were anticipated. All of them came from clean, well-calibrated instruments on a spacecraft that functioned exactly as designed until the moment it entered Saturn's atmosphere. But the most extraordinary finding tied to this mission does not come from the spacecraft's final orbits at all. It comes from measurements it made of a completely different object, and from what a completely different telescope confirmed about those measurements 6 years after the spacecraft was already gone. Enceladus is Saturn's sixth largest moon, roughly 500 kilometers across, covered almost entirely in fresh, bright ice that makes it one of the most reflective objects in the entire solar system. Back in 2005, this spacecraft discovered that Enceladus has an active geological process happening at its south pole, a set of long parallel cracks in the ice surface called tiger stripes, from which enormous plumes of water vapor and ice particles are erupting continuously into space, creating the material that forms Saturn's faint E-ring. This discovery was immediately extraordinary. An active, geologically driven process on a moon the size of Enceladus required an internal heat source, because Enceladus is too small and too far from the sun to be heated significantly by solar radiation. The heat driving those plumes is generated by tidal flexing. The gravitational tug between Enceladus and Saturn, combined with the influence of other moons, including Dione, creates a rhythmic squeezing and stretching of the moon's interior that generates heat through friction. That heat is sufficient to maintain a liquid water ocean underneath the ice shell, with the tiger stripes serving as the direct pipeline between that ocean and the surface, an internal liquid water ocean in a body far beyond the sun's habitable zone. This single discovery changed the definition of where in the solar system life could potentially exist. The spacecraft went on to make many more passes through Enceladus's plumes, analyzing their chemical composition in fine detail. The plumes contained water ice. They contained simple organic compounds. They contained molecular hydrogen, and the presence of that hydrogen was particularly significant because molecular hydrogen in the plumes indicated that hydrothermal reactions were happening on the ocean floor, where hot water from the rocky core was reacting with minerals in a process called serpentinization. Hydrothermal systems on Earth's seafloor support rich communities of life that are entirely independent of sunlight. The discovery of hydrothermal activity inside Enceladus's ocean was one of the most significant astrobiological findings in the entire history of space exploration. By 2017, when the mission ended, the chemical inventory of Enceladus's plumes included water, molecular hydrogen, carbon dioxide, methane, and various other organic compounds. Scientists noted that 5 of the 6 elements considered essential for life as we understand it, carbon, hydrogen, nitrogen, oxygen, and sulfur, had all been identified in the plumes. One element was missing from the confirmed list: phosphorus. Phosphorus is not some trace element in the context of life. It is a fundamental structural component of DNA and RNA, the molecules that carry genetic information in every known living organism. It is the backbone of ATP, the molecule that stores and transfers energy inside cells. Without phosphorus, life as we know it is not possible. Finding phosphorus in Enceladus's ocean would complete the inventory of life's essential elements and remove the one remaining chemical objection to the possibility of living chemistry existing inside that ocean. This spacecraft was not able to confirm phosphorus in Enceladus's plumes during its active mission. The mass spectrometry instrument it carried was not sensitive enough to detect phosphorus compounds at the concentrations present in the plume material during its flybys. In June 2023, 6 years after the spacecraft fell into Saturn, the answer arrived from a completely different direction. A planetary scientist at the Free University of Berlin, who had worked with the archived mass spectrometry data for years, led a team that went back to the original data archive and reanalyzed it, using improved techniques and a far more complete understanding of how the instrument responded to specific compounds. Inside ice grains captured from Enceladus's plumes, sampled and analyzed years earlier, the team found phosphorus, not just traces, concentrations of phosphate compounds orders of magnitude higher than those found in Earth's oceans. Phosphorus in Enceladus's ocean at high concentrations, in the same water that is already chemically active, hydrothermally heated, and already known to contain every other element biology requires. The paper was published in Nature in June 2023. The team noted that the finding completes the inventory of the key elements necessary for life as we know it inside Enceladus's ocean. The James Webb Space Telescope independently confirmed aspects of Enceladus's plume activity in new observations that showed the plumes are even more extensive than the original measurements had indicated. The water vapor extends into a vast cloud spanning the entire E-ring that the original mission had not fully mapped. The spacecraft found the ocean. It found the heat. It found 5 of the 6 elements. Scientists went back to its own data and found the 6th. The ocean beneath Enceladus's ice now has a confirmed chemical inventory that satisfies every known prerequisite for the emergence of life as we understand it. Whether life is actually there is unknown. There is no observation that confirms biological activity. The presence of the ingredients does not guarantee the product. But the distance between we don't know if the ingredients are present and we don't know if the chemistry has assembled into life is the entire scientific journey, from the discovery of the plumes in 2005 to the phosphorus paper in 2023. Life was not found. What was found is something more rigorous and more scientifically durable than any single splashy detection of life could ever be. It systematically established the physical and chemical conditions that make life possible in a place that, before 2005, nobody had any reason to look. Return to Saturn itself for a moment, because the real story here is not just about Enceladus or about the ring-atmosphere gap chemistry. It is also about how little we actually understood the planet that is visible to the naked eye from Earth. A planet humans have been observing since before the invention of the telescope, and one we had an orbiting spacecraft studying in detail for 13 years. Saturn emits significantly more energy than it receives from the Sun. This is not unique to Saturn. Jupiter does the same thing, but the mechanism is not fully understood for either planet. On Jupiter, the excess heat is thought to be primordial, released as the planet slowly contracts under its own gravity in a process that has been ongoing since Jupiter first formed. On Saturn, this explanation does not work as cleanly because Saturn is smaller and should have radiated away its primordial heat much more quickly. Several alternative mechanisms have been proposed, including the slow separation of helium from hydrogen deep inside Saturn's interior, a process called helium rain, where droplets of helium fall downward through the hydrogen mantle, releasing gravitational energy as heat as they descend. But the models for this process do not quantitatively reproduce the observed excess heat at the level of precision the data demands. Saturn's atmospheric dynamics, measured in unprecedented detail across 13 years, showed features that kept surprising atmospheric scientists throughout the mission and long after. The hexagonal polar storm has been studied in detail by instruments that did not even exist when Voyager first photographed it. The storm is not just a persistent hexagonal shape. It contains jet streams, wave structures, and embedded vortices that interact in ways atmospheric fluid dynamics models struggle to fully replicate. The exact mechanism that produces and sustains a persistent hexagonal shape in a planetary atmosphere rather than the circular or oval shapes that more commonly appear is still an active area of research. A major storm that erupted in Saturn's northern hemisphere in 2010 and 2011, the largest and most intense storm observed on any planet since the Voyager encounters, was studied in a level of detail impossible from Earth. The storm circled the entire planet within months. And as its evolution was tracked, the data showed chemical signatures in the atmosphere produced by the storm dragging material up from deep inside the atmosphere to high altitudes. Some of those chemical signatures, particularly involving water and phosphine, were difficult to explain with the standard models of Saturn's atmospheric chemistry and mixing. Phosphine on Saturn. In 2020, the detection of phosphine in Venus's atmosphere triggered enormous scientific controversy and public attention as a potential biosignature. On Saturn, phosphine has been known to be present for much longer, and its abundance in the upper atmosphere has been a standing puzzle because the chemical should be destroyed by the ultraviolet radiation in Saturn's upper atmosphere faster than it can be resupplied from below. unless it is being resupplied more efficiently than the models describe, or unless the destruction process is slower than calculated, or unless there is a production process operating in the atmosphere that has not been identified. None of these questions are resolved. All of them are open. All of them are being actively worked on by planetary scientists using this mission's data, and increasingly by researchers hoping to design future missions that can provide the extra measurements needed to test the competing hypotheses. The actual story of that spacecraft's final moments, the genuine, documented, peer-reviewed story, contains no alien signals. It contains no quantum AI decoding hidden messages. It contains no cover-ups or missing encrypted images. What it contains is something that is, in the genuine scientific sense of the word, more profound. It contains the systematic demonstration that a planet we have been studying for 4 centuries still has fundamental properties we do not understand. It contains the discovery of a moon with an ocean that has every chemical ingredient life requires. It contains measurements of a ring system that is more chemically complex and more dynamically active than any model had predicted. And it contains a magnetic field puzzle that challenges the theoretical frameworks planetary scientists use to describe how every other planet in the solar system generates its magnetic field. These are not comfortable findings, but they are not the kind of findings that let the people who study Saturn say, well, we understand that now and move on. They are findings that expand the questions rather than shrink them. They are findings that make Saturn more mysterious, not less. After 13 years of dedicated observation by the most sophisticated spacecraft ever sent to the outer solar system, on September 15, 2017, at 7:55 a.m. Eastern Time, its signal was lost as the spacecraft entered Saturn's atmosphere at 111,000 kilometers per hour. The science team at the Jet Propulsion Laboratory watched the signal strength hold until atmospheric drag became too great for the spacecraft to maintain its antenna pointing, and then the signal simply stopped. Engineers and scientists who had spent years of their careers on the mission were openly emotional. Some cried. The mission had been a 13-year relationship with a distant system, and it ended in 91 seconds of final data transmission before the spacecraft carrying the instruments was vaporized. But the data it had sent home over those 13 years, including the final grand finale measurements still being analyzed today, did not stop being scientifically productive when the signal ended. The mission ended on September 15, 2017. Its science did not. The phosphorus discovery came in 2023. Papers on the ring chemistry are still being published. The magnetic field alignment puzzle is still open. The Enceladus Ocean is still one of the most active topics in astrobiology, and the James Webb Space Telescope, which began science operations in 2022, has added new observations of the Saturn system that complement and extend those older measurements, including images of the vast hydrogen cloud surrounding Enceladus that stretched far beyond anything the original mission had mapped. When the team found phosphorus inside archived data in 2023, they were using instruments and analysis techniques that did not even exist during the active mission. This is one of the most important things about space mission data. The raw numbers sit in archives, and as our tools for interpreting those numbers improve, the archives keep yielding findings the original instruments were quietly collecting, but that nobody was equipped to see at the time. There may be more inside that archive. Almost certainly there is more. The question is, what questions need to be asked and what tools need to be built to find it? If the real story, the documented, peer-reviewed, genuinely extraordinary story of what this spacecraft actually found and what scientists are still learning from its data is the kind of thing you came here for, subscribe right now and turn on the bell. The next Saturn mission is still in the planning phase. Several concepts have been proposed and studied. The most advanced is a proposal for a return to Enceladus, specifically a dedicated mission designed to fly through the plumes, with instruments capable of looking directly for signs of life, rather than just the chemical conditions that make life possible. Such a mission would carry mass spectrometers an order of magnitude more sensitive than the old ones, capable of detecting amino acids, lipids, and other complex biological molecules if they are present in the plume material. That mission has not been selected or funded as of 2026. The scientific community has been making the case for it for years, and the case rests on what this mission found. The ocean is there. The heat is there. The chemistry is there. The only question the instruments we have sent so far cannot answer is whether anything is living in it. That is the answer a future mission to Enceladus would try to provide. And the foundation on which that future mission will stand was laid by a spacecraft that plunged into Saturn's atmosphere on a September morning 9 years ago, transmitting data for 91 seconds as it burned, sending home the last readings of a 13-year conversation between human science and the second largest planet in our solar system. The conversation ended. The questions it left behind have not. Stay with us. They are still being answered.